So now you're all up and refreshed. It's time to introduce the first keynote. It's my pleasure, and it's always fun to see his talk and the content that he will bring. But it's my really pleasure to introduce you Mark Reinhold as our first keynote speaker. Mark, it's all yours. Welcome to DevOps.
Thanks, Stefan. Good morning. It's great to be back. The Java platform, for those of you who don't know, is 18 years old. If it were a person, it could purchase alcoholic beverages in most countries. Java is a descendant of an experimental language called Oak that was designed for a handheld computer called the Star 7 that's incredibly primitive by today's standards, but which was well ahead of its time back in 1992 when it was built. If you follow the link on this slide, you can watch this great video of James Gosling demonstrating this device, complete with an animated Duke avatar and the same physics-based scrolling model that you find in modern smartphones. As Java has grown up, it's served us well in many different kinds of devices. Feature phones, TV set-top boxes, desktop computers, and big iron servers. It's been used to write many different kinds of applications on those devices. Games, applets, desktop client applications, and enterprise web applications and backends. Now, of course, it's been more successful in some of these areas than in others. As it stands today, Java is a family of 3 comprehensive platforms: Mobile Edition, Standard Edition, and Enterprise Edition, which are used daily by over 9 million developers worldwide. Which leads us to a question. Is Java all grown up? Is it time to stop working on it? Are we just done? No technology can survive by standing still, and Java is no exception. That answer, of course, leads us just to more questions. What motivates the further evolution of Java? What are our goals, and what principles should guide us along the way? The main goal of Java moving forward should, I think, be the same as it has been from the very beginning, and that is to maximize developer productivity. Oh, and also have fun whenever possible. To do this, we will, as in the past, add new features to the platform in order to address new types of devices, take advantage of new hardware capabilities, and address new application areas. We might also sometimes take old features away. Now, this is hard. We can't just pile on feature after feature after feature after feature. For Java to continue to thrive, we must maintain what James Gosling called the feel of Java, as reflected in its core principles of readability, simplicity, and universality. For an example of how we've added features in a careful, considered manner in a way such that they relate to each other well over a period of time, let's talk about hardware. Due to the fundamental laws of semiconductor physics, multi-core processors are here, whether we like them or not. This has presented a challenge to every established programming platform. In the case of Java, writing programs that can effectively leverage many processor cores was tricky at best prior to Java 7. Given only threads and locks, which are incredibly primitive, great care was required, along with hundreds, if not thousands, of lines of code. Now, fortunately, it turns out that many parallel programming problems can be described as data parallel. A data parallel problem can be solved in a divide and conquer style, in which you recursively split it into smaller problems and then split those problems into smaller problems and so forth, until each remaining problem can be solved in a very short amount of time. You then combine the answers for each subproblem in order to compute the result of the original problem. The beauty of data parallel problems is that this recursive decomposition process makes it possible to spread the computation naturally across a large number of processor cores. Getting all the details right is still rocket science, so in Java 7 we added an API called the fork join framework to make this much simpler. All you have to do is specify how to split a problem into subproblems, how to solve them serially, and then how to combine the results back together. The fork join framework is definitely an improvement over raw threads and locks, for data parallel problems. But being a framework, it has the usual problem of frameworks, namely that you have to spend a fair bit of effort on code that does nothing really but kind of feed the framework. Here's an example of a very simple use of the fork join framework. The code in orange is the only code that's actually specific to the problem to hand. So from the standpoint of code readability, and hence long-term maintainability, the style of API can make programs easier to write, but in the long term, much harder to read. So that's why, almost exactly 4 years ago, I stood pretty much right here and said, it's time to add closures to Java. For technical reasons, we call them Lambda expressions now, but that's really just a detail. I instigated this work, but Brian Goetz made it happen, and I could not be more pleased with the end result. Brian?
Thank you, Mark. Yeah, we need number 2. Yep. Perfect. All right, so as Mark said, I'm going to talk a little bit about the work that we've done that's led up to Java 8. But before we talk about where we're going, I want to talk a little bit about where we've been. So hopefully this won't just be a boring history lecture, but we'll shed some light on some of the aspects of Java that some of us might be unaware of, and also talk a little bit about the challenges of stewarding what is the world's most popular programming platform. So I'm going to start at the time at which Java was invented. So 1995, the programming landscape was dominated by Fortran for scientific computing and by C for everything else. Now, before then, it hadn't always been like this. There was a polyglot period that preceded this when people could use whatever language they liked, to solve their problem. But the support behind C consolidated really quickly, largely because the compiler itself was so portable because it was based on a relatively small and easy to port runtime. And for me, and I think for a lot of us that were programming at the time, this was kind of disappointing. C could get the job done, but it was rarely the right tool for the job. And I had the pleasure of taking the Abelson and Sussman scheme class at MIT in the 80s, and I was really excited. It painted this picture of this bright, shining computational future that I couldn't wait to be part of, and boy, was the real world a disappointment. So there was, even at the time, there was definitely a need for something better than C, but we were all fighting against the, well, we all use C because we all use C. So in looking at something that's been successful, it's often informative to look at how inventors describe their technology at the time, not because this actually tells you anything about the technology, but it tells you a lot about the problem that they thought that they were solving. So Java was supposed to be a blue-collar language, one for working programmers to get their job done, not an ivory tower invention for writing perfect code. And of course, there was plenty of hype. At the time, Java was described as a simple object-oriented, distributed, interpreted, robust, secure, architecture-neutral, portable, high-performance, multi-threaded, dynamic language. Now, there's plenty of buzzwords here, but I want to drill into 2 of them. One of them is interpreted, and no one actually ever intended Java to remain an interpreted language. That was an artifact of the 1.0 implementation. But even at that time, there were JIT prototypes, and everything about the design was influenced by JITability. But there was no buzzword for virtual machine-based in 1995. So we fell on proxies for that, like interpreted, and also secure. But the value of building on a virtual machine is probably obvious today, but at the time it was pretty risky, and I'm going to talk a little bit about some of the risks. The other interesting one is dynamic, and this might be surprising to people. A lot of people would not describe Java as a dynamic language. They would say, oh, Java's a static language. So to hear it described by its inventor as dynamic might be a little surprising. I think the reason this claim is surprising is that we have this kind of broken mental model for what is static or what is dynamic. And we imagine this Boolean as Java is static, Ruby is dynamic. But that's really a simplistic model. There's really more of a spectrum between static and dynamic. So maybe a better way to model this in code, because this is, of course, how we think, right, is how dynamic is this language? Ruby is more dynamic than Java. But this is actually a pretty simplistic notion as well. The reality is, there are many axes of static versus dynamic. Static versus dynamic just means the balance of what code is done at compile time or build time versus at runtime. And so the most obvious axis of static versus dynamic is typing, but there's quite a few others. So when are dispatch decisions made? When are linkage decisions made? When can we interrogate the program about its types? When do we get to load new classes? And so there's quite a lot of different axes on which you might measure how dynamic a language is. So let's see how Java stacks up in this static versus dynamic space. And it turns out Java is more dynamic than we all think it is. A lot of things happen statically in Java, like typing, but a lot of those same things happen dynamically too. So typing happens at compile time and at runtime. So if you try to stick an integer in an array of strings, you'll get a array store exception. That's dynamic typing. The dynamic type system is a different type system than the static one. But they're both there, and they both serve different purposes. They both catch errors that the other does not. Similarly, Java does compilation statically, and it does compilation dynamically. We do method overload selection statically. That's probably the most static aspect of Java. But then we do dynamic linkage, which is really dynamic. And this is this is what allows us to compile our program and then run it against a different version of the jar that we compiled against and have everything just work. So dynamic linkage is a really, really big deal. We also have a dynamic type checking verifier, and we dynamically enforce accessibility constraints. So there's an awful lot going on at runtime. And the list goes on, right? We support dynamic introspection in the form of reflection. We support dynamic class loading. So on this scale, Java does look pretty dynamic, even though the type system itself, which is what programmers see every day, is fairly, is static. Now, a lot of these forms of dynamism existed in 1995. Unix and Windows had dynamic link libraries, already, but dynamic linking was always the exceptional path. So when James said Java is a dynamic language, what he was really pointing to was turning a lot of the conventional wisdom of when certain things happen upside down. So if you look at the feature list of Java in 1995, it really looks to be kind of an odd mix. And it may not be obvious from today's perspective, but a lot of these features were really risky. And so Java made this huge bet that the performance of garbage collection and dynamic compilation would improve quickly enough for Java to be more than a toy. And I mean, this is, obvious in hindsight, right? Fast forward today, the performance of Java, routinely blows away almost everything else, from the so-called dynamic languages like Ruby or JavaScript, and even the performance-oriented static languages like C++. But in 1995, garbage collection and JIT technologies were sort of academically understood, but they had yet to be proven in a mainstream industrial language. Similarly, there were an awful lot of features borrowed from academic languages, such as dynamic linking, integrated thread support, and a formal memory model. And so this is kind of a little bit strange given the claim that James made that Java is a blue-collar language. Now, a lot of these turned out to be pretty good bets, but at the time they were really risky, and they hadn't been proven in languages that had gotten any kind of real industrial traction. The list of risky things, goes on. We had this intense commitment to safety with like runtime type checks and runtime bounds checks and runtime null pointer checks, which like totally were going against the C trends of the day. And it was not obvious at the time that dynamic compilers would make all these costs go away, which eventually they did. On the other hand, there was this almost Luddite undercurrent of we don't need that when it came to the programming model. So Java the language made all of these decisions that were kind of the opposite decisions from C++. We don't need no stinking operator overloading. We don't need multiple inheritance, or at least not C++'s multiple inheritance. We don't need structs or macros or function pointers or even pointers at all. So this kind of leads us to the question, was James just smoking something? It just seems like this random grab bag of some wacky stuff from this academic language and some wacky stuff from that academic language, all at the same time, claiming to be blue collar, and some, a healthy dose of boring conservatism in the language design. So how do we balance this? How do we square the wacky stuff with this blue collar claim? So Java was explicitly saying we're not an ivory tower language, and yet so many of the features were taken from ivory tower languages. So was this just James's pet fantasy that happened to work out? Well, if you drill a little bit deeper, you'll see that there's a stratification. all the risky stuff is going on in the VM, where we don't see it. And all of the we don't need any of that stuff is happening in the language at the surface. And this wasn't an accident. So when I asked James about it, he said, it was clear from talking to customers that they all needed garbage collection, dynamic compilation, dynamic linkage, threading, and all of these other things that had always come wrapped in languages that scared them. So, I mean, Java really had more in common with Lisp or Smalltalk or other scary languages than it did C or C++. But it looked like C++. It looked like C++ just enough to make people comfortable. So people thought they wanted C, but really they needed the features of languages that scared them. So James called this the wolf in sheep's clothing. We gave people the features they needed in a language that looks like what they thought they wanted. It's like the mother of all Jedi mind tricks. It was great. And there's a lesson here, which is if you want to change the way people program, you want to get a large group of people to up their programming game, scaring them is not the way to do it. Okay, so let's fast forward to where Java is today. So I promise this is the only marketing slide here. Java is arguably the world's most popular programming language and the world's most popular programming platform. We have a developer community of over 9 million developers. And I don't bring this up to boast, but because this success really places a lot of constraints on us as we evolve the platform. So as Mark said, we can't just stand still. That's a recipe for being irrelevant. We also need to evolve very carefully because even the smallest change could break someone's mission-critical code. So I'm going to talk a little bit about what constraints this imposes on us in how we evolve the platform. In a community of 9 million people, there's going to be a lot of different opinions. There's going to be a lot of separate interests to be balanced, and it's not always easy to keep everybody happy. So in evolving Java, we face this constant tension. The world is changing around us, and we have to respond to that change, or we become irrelevant. But if we change too fast, the risk is we lose touch with the principles that we started with and the customers that got us where we are. So there are these forces pushing us towards change, keeping up with changing hardware reality, keeping up with changing developer expectations, keeping up with changes in developer demographics. And also, of course, you can't survive for 18 years and not make a few mistakes, and we'd, of course, like to fix some of those mistakes of the past. On the other hand, they're forces that push us to resist change. We have a very low tolerance for changing anything that would break people's code. We don't want to buy into developer fashion of the week because we don't want to alienate our loyal users who may like things largely as they are. And so just like in politics, it's possible to be hated by both sides, right? One side says, you're changing too fast. The other side says, you're not changing fast enough. So if we want to not alienate our core users, it's a good idea to have some core principles. So the language, which was fairly minimal in terms of its feature set when it was designed, was driven by a pretty reasonable set of principles. And these are principles that we've gone back to time and time again as the language has evolved. So this list here was enumerated by Graham Hamilton, who was the feature gatekeeper for the Java language for its first 10 years. And these principles have done pretty well for us so far. The most important one is the first one. Reading code is more important than writing code. Now, personally, I'm constantly amazed at how many people don't get this even today. We write code once, but we read it many times. When we're writing code, hopefully we're thinking about it, which means we have some time. We're not limited by the rate at which our fingers can move. But when we're reading it, we're often in a hurry. We're trying to fix a bug. We're trying to figure out how something works. And so we should always err on the side of making code more readable. The easier code is to read, the more successful our interactions with it are going to be. Now, the last principle here is related. It's about transparency. Code should do what it looks like it does. Okay? So these have been principles that have sort of guided us and served us well in the evolution of Java for a long time. So let's take a look at where things were a few years ago when we started planning Java 8. So it's pretty clear the language was looking a little bit long in the tooth, and certainly developers had more expectations than they did a few years prior, some of them even without leaving the JVM. So we definitely wanted to keep up with developers' productivity expectations. Though even within the community there were disagreements about how much change was enough or how much change was too much, and we knew whatever we did would make some people unhappy. But we have to remain relevant with respect to today's hardware reality. So a key challenge we faced was finding a better programming model that supported both sequential and parallel execution while at the same time still being Java. We sort of took this as one of the central challenges for the Java 8 language and library features. So let's actually look at the feature list we chose to implement for Java 8. It's actually pretty short. People say, oh, Java is changing so much in 8, but the feature list of things that we're adding is not that long. Lambda expressions, some more type inference, a mechanism for evolving APIs over time, and some new library support for aggregate and data parallel operations. Now, a lot of the ideas here even, like Lambda expressions, are already familiar to those who have used other languages. How many people here have programmed in JavaScript? Ruby, Python, Lisp. See, most of you already know what Lambda expressions are. This isn't, this isn't anything radical and new. So the features really aren't the interesting story. The interesting story is how did we deal with the constraints of doing these in a way where we get a result that still feels like Java. Of course, one thing that helps is to pick your features carefully. So we focused on a handful of features that we hoped were the right ones. In a sense, all the features on this list were simply the consequence of choosing to add Lambda expressions to the language. The interesting part is the single largest part of the work was in an area of the language that no one ever sees. It was overhauling the interaction of overload resolution and type inference, which allowed us to support using lambdas in a natural way. And these features have almost no surface area at all, except the ability to write the obvious code and have it work the way you expect. So the only time you notice these things is when something goes wrong. So a lot of you, as you've just demonstrated, already know what a lambda expression is. It's an anonymous method. So it's a simpler way of writing a method. The key point is it's finally time, or actually well past time, for Java to have them, in part because a lot of other languages already do. The key aspect of lambdas that we care about is that this is what enables us to treat behavior like data. And this changes the nature of the kind of libraries we can write. So libraries have always been a big part of Java's strength, and language features like lambdas are not an end unto themselves. They're a means to an end. Among other things, they're a multiplier for the effectiveness of libraries. Having lambdas in the language lets us write libraries that are more powerful, and that's not actually the goal either. That's just a means to the real end, which is to make developers' lives simpler, to write more expressive, easier to read, less error-prone code. And if that new and improved code happens to be more easily parallelized, well, that's even better. So let's look at the before and after. Developers, could always model code as data using anonymous classes, but it was painful. So as a simple example, imagine we're writing a method to remove all the elements from a collection that meets some criteria. So we do the obvious thing that that we do in Java. You model the criteria using an interface like, say, predicate here. And then, you write a method that takes a collection, it takes a predicate, and it removes the elements that match the predicate. And that's all well and good. The problem, as all of you have probably experienced, is when the rubber meets the road, the user had to write an anonymous class to actually implement the criteria. And this works, but is kind of ugly. And it's really easy for the intent to get lost in the syntactic noise. So, as a result, people didn't write APIs like this because using them was too painful, because there was just so much boilerplate code that we had to write. Most of the syntax associated with inner classes is just boilerplate. But if we replace the inner class with a lambda expression, the meaning of the code becomes a lot more clear. So again, lambda expression, simply just an anonymous method. It has everything a method has. It has an argument list and a body. It has a return type. The arguments have types. It has a list of thrown exceptions. But it's written a lot more syntactically compactly. So it does the same thing as the anonymous instance we had before, and the code is certainly more compact. But an interesting thing happens, which is this changes the APIs that we're willing to use, and that in turn changes what APIs we're inclined to write. So what might have started out as a quantitative decrease in pain, I can write this same thing with less code and it's more readable, actually turns into a qualitative change in the APIs that we actually end up writing. I should also point out that the implementation of Lambdas is not just syntactic sugar for inner classes. There's an awful lot of VM work that goes into making them faster than inner classes, and I'm going to be talking about that this afternoon, I think at 12. So I have to make a quick note on syntax, because everybody likes to talk about syntax. Endless arguments over syntax. We basically picked the same syntax as C# and Scala. We went through kind of a search for, is there something obviously better? We didn't find anything obviously better, and we went with what worked in other languages. Okay, so here's the interesting part. When we replaced the anonymous class with a Lambda, you notice we didn't change the API of remove all. So this is an example of how having billions of lines of code out there is going to affect your decisions and may push you to make different choices than you might have made. We could have added function types to the type system. In some sense, that was the obvious thing to do and kind of our first thought of what we should do. And it also turned out to be the wrong thing to do. If we had done function types, they would have interacted with some existing features of the Java language in a bad way, namely boxing and erasure. And so what we did was we leveraged an existing pattern, which is describing functions with these one-method interfaces like runnable and comparator, which we've been doing for years. And the real effect of this is that all of these libraries out there that use this pattern are immediately forward compatible with Lambdas, even though they never imagined that the language would ever have Lambdas, and still can take use of this pattern. So libraries we wrote 10 years ago that use single method interfaces to describe behavior can be used immediately with Lambdas. And a result of that is we avoided bifurcating the world of Java libraries into old and new, which would have been this huge waste of effort as we migrated all our libraries. So good story, but people often ask, why did it take you so long? I mean, after all, we knew 3 years ago what idioms we wanted to support. We knew what features we wanted to have. Where was the time-consuming part? Well, the time-consuming part was making it all seamless. Like I said earlier, the biggest part of this was working through the interactions of method overload selection and type inference. If we hadn't done that, it would have looked nailed on. And we wanted it to not feel nailed on. We wanted it to feel like an integrated part of Java. So we knew what the feature exactly was, a long time ago, but it took a while to work through the details. Okay, so we talked a little bit about how this affects the kind of libraries we actually do write, so let's look at an example. So we're integrating support for Lambdas into the collections, and here's some code that illustrates a typical query over collection. You have a list of people. You want to find the weight of the heaviest man. Now, if you've programmed in other languages, this may look familiar. Almost every language that has Lambdas has similar features in their library. So you've probably written code like this in Ruby or Python. And you could have written APIs like this in Java 10 years ago, but we didn't because it would have been too painful. So a big goal was reducing the pain of expressing this sort of computation in Java. But there's this hidden bonus here now. By having recast the computation into a more functional style, parallelism gets easier also, because what we've done is we've inverted the control of what's going on. In the old way, the client was in control of the iteration. But this way, the library is in control of the iteration, and the library is free to use parallelism or out-of-order execution, in order to get the job done. So, we've made this, a lot easier, to choose between sequential and parallel simply by making small changes to the code rather than having to rewrite your code, in the fork join framework that, that Mark showed you. So if we want to do this computation in parallel, we just change stream to parallel stream, and we get a parallel stream out of the collection. Now, again, something we still could have done with fork join, but the code would have been very different. It would have been more painful to write, and that's a hurdle to put in front of developers that we didn't want to do. So if you frame the computation correctly, the serial and parallel expression of that computation are very similar, and we don't get distracted by all the accidental complexity of the implementation details. And this, in turn, reduces errors because when the code looks like the problem statement, it's more likely to be right. So as I've noted, the library I've just shown you a very brief example of, and there's a lot of talks here at Devoxx that, that will go into more detail. Paul Sandoz will have a talk this afternoon called Streams in Full Flow that'll go into this API in excruciating detail. this is nothing new. We've seen this in a lot of other languages. But where it really does move the ball forward is in parallelism. So I want to just give you a sneak peek of where some of the inspiration came from. If you've not seen this presentation, it's a wonderful presentation by Guy Steele. It's available online. I encourage you, go watch it tonight. And if you've seen it already, go watch it again, because I learn something every time I watch it. He asks this simple question. Normally, when we express a for loop, this particular one is in Fortran, but Java is basically the same, we get a computation tree that looks like this. Really, what we would like is a computation tree that looks like this. And the question is, what kind of code do we want to write in order to get this kind of parallelization? And I think we have a pretty decent answer to that question now. So again, the code looks pretty simple, and other languages have done this before, so, well, why did this take us so long? It was obvious we wanted to do MapReduce computations on collections from the beginning. The other 2 years was taken up by a lot of details, getting all the flexibility and performance we wanted, and making it feel, baked in. So, for example, all data structures and all collections in the library, as well as arrays and other sources, can be decomposed and acted on both sequentially and in parallel. So we introduced this abstraction called splitterator, which is a combination of iterator and the splitting that's needed for parallel decomposition. Cute name. And we retrofitted this onto all the collections, and we made a way so that you can get a splitterator for an array or for a generator function or an I/O channel, so that any data source can act as the source for either a sequential or parallel stream. And then we implemented all the stream operations that can work sequentially or in parallel against any source, because they're all just implemented in terms of this abstract splitterator model. Now, if you look at the computation, you might think that what we're doing is making 3 passes on the data and populating intermediate data structures with the results of the filtering and mapping. But in reality, there's no intermediate result. The computation is fused automatically into one pass, whether sequential or parallel. And this is all hidden from the user without having to think about the details. And then finally, we take advantage of information that we know about the source. If we know that the source, the elements are unique, or the elements are sorted, or we know something about its size or its splitting characteristics, the implementation can use that to optimize the execution. And so the bottom line here is you can do a parallel MapReduce query on a plain old non-thread safe array list without having to switch data structures, because all your data is in array lists and hash maps anyway, so we didn't want to make people change their data structures to get parallelism. So it's a pretty cool story. All right, so you might be thinking, all right, this is really cool, but honestly, the imperative version of the code I showed you wasn't so bad either, right? And that's true. I mean, it would have been a for loop with, about as many lines of code, actually. The real issue is that the imperative version just doesn't scale very well as the problem gets bigger. So if we take a more complex query, like find me the transactions to a buyer who's over 65 and print the sellers in order of name, we could write that in Java like this. I don't expect you to go through the details, but it's kind of a typical, Java code that grovels over collections. And the key is, if I gave you 5 seconds and said, tell me what this code does, you probably wouldn't get all the way through it, because you'd be lost in the details. So if we recast this computation using the streams library, the code becomes a lot more clearer, and it reads a lot more like the problem statement. Take the transactions, get the ones whose buyer is over 65. For those, get the seller, throw away the duplicates, sort them by name, and print them out. Very clear, much less error-prone, and parallelism for free. So as we scale up from toy problems to real-world problems, the power of this approach really shines. What we're doing is, even though you have the choice to keep doing things the way you've always done, these new libraries give you the opportunity to raise the level of abstraction of your computation, operating on a data set as a whole rather than an element at a time. It encourages you to express what you want to do, not how you want to do it. And as a result, the code starts to read like the problem statement. It doesn't leak all these extraneous details like these intermediate collections, and you get parallelism for free. So I think that's a pretty good story. And so what we've done here, actually, is we've kind of taken a little page from history and pulled the wolf trick again. A lot of people, look at lambdas as just another language feature, which they are, but, in reality, they're an enabler for a more functional style of programming in Java. Without being too pushy, we're not taking away the old features. We're not saying, thou shalt do it this way. You can still do it the way you've always done if you want. But what we hope is over time, developers will realize that the functional idioms are often easier and better, and they'll slowly migrate out. And so the lesson here is if you want people to change what they're doing, don't scare them. Make the path of least resistance lead to the right result. And then people's natural laziness will just bring them to the right place automatically. So, we don't even use the word functional, right? People don't have to know that they're doing functional programming. As some people in this room may have discovered, selling functional programming to the mainstream is hard because it's full of scary words like monad and catamorphism. But you don't need people to buy into the religion. You just need for them to look at the code and say, yeah, that's a better way to do it. I think I'll do it that way. Okay, so let's talk about the last feature we added in Java 8, which is default methods. This feature addresses another problem new languages don't have, which is how do we compatibly evolve old APIs? When your language is new, your APIs are new also, and you're probably not going to be thinking, well, what's going to happen in 10 years? You're still hoping that people will buy it at all. So interfaces in Java are this double-edged sword. On the one hand, they make these really strong contract guarantees, but on the other, you can't add a new method to old interfaces without breaking implementations. And this isn't a problem in year 1 or year 2, but we're going on 15 years with our collection APIs, and it's a big problem. If we were designing our collections today with lambdas, they'd look completely different. And so the perverse result of having added lambdas to the language is now that our aging libraries look even older. Great. But the collection libraries are so deeply embedded in the JDK and in all of your Java code that migrating to new collections would be a huge effort. So we needed a means of evolving interfaces over time. The idea is pretty simple. We want people to be able to add new methods to an interface, virtual methods, and in order to do that without breaking existing implementations, you have to provide a default implementation. So the code is actually pretty simple. It looks like an interface method with a way of saying this is one of these new default methods, and it has a body. And anybody who doesn't override that method just inherits the default body. Now, this is a feature that depends on something I talked about earlier, dynamic linkage, because you might be invoking a method on a class that didn't exist at the time the class was compiled. So these default methods, fully virtual methods, they can be overridden. Clients can't even tell from the outside, except using reflection, that the method is any different from another interface method. So as a kind of bonus, while the primary goal of default methods was interface evolution, it also just happens that interfaces now become something like stateless traits. So that's kind of nice. That's a powerful tool. Is this what we would have designed if we were starting from scratch? Maybe not. But we have a lot of Java code out there. We have a lot of Java programmers who understand interfaces. And this adds a lot of power while being only a small deviation from where we are now and remaining compatible with all the Java code that's out there. Okay, so the set of features we could have added to Java is enormous, but it's not about number of features. It's about what those features enable. So the feature set in Java 8 that we've added, I think, like I said, is pretty small. The hard part, and the reason it took 3 years or 6 years or 15 years, I guess, depending on how you count, was fitting it all in so that it looked like it belonged. And this included working through the interaction with all the features that came before, including serialization. So the lesson here is, with enough effort, it is possible to teach an old dog new tricks. And with the leverage of 9 million developers who can benefit from those new tricks, it's really worth the effort. Okay, so the obvious question people ask at this point is, well, is there anything left to do? Or are we ready to just wrap a pretty ribbon on it and call it done? Well, there's a lot of pain points left, and we want to systematically address those. So, for example, people still struggle with the pain of boxing, with the lack of tuples, the inconvenience of erasure, the inability to generify over primitives, and many, many limitations of arrays. These are all old problems, but a lot of them are put into starker contrast by the work we've done in Java 8. If Java 8 represents a mild turn towards the functional for Java, the lack of other conveniences functional languages offer, like tuples, start to become even more obvious. And we can add to our list of challenges those posed by new execution targets like GPUs. And again, Lambdas are a good first step in being able to write GPU code, but there's way, way more. So just, kind of peering into the crystal ball a little bit, and of course, don't hold me to this. This is just, I'm just talking here. The underlying problem, I think, behind most of these pain points is Java's overdeveloped sense of object identity. So we have this runtime type system where we have objects and arrays that have identity, and then this handful of magic types like int that we can do cool things with, like stuff them into registers or push them onto stack slots, but we can't generify over them. We can't describe them with type variables, and there's no way to make new types like like primitives. We can't make complex types or 128-bit int types or anything like that. So there are times, quite a lot of times actually, when we really only care about the data and not the identity of the box that it comes in. And like a lot of other things, it probably would have been easier to design this in from the beginning than to retrofit it afterwards, but here we are, and the question is, what are we going to do about it? So the key challenge here is dealing with this assumption of everything is an object with identity. For example, every object in Java can be used as a lock or as a condition queue and has identity-based operations like identity hash code or identity equality. So what we want to do over time is expose a means, probably first in the JVM and then the language, to describe aggregates without identity. And it turns out that this is the key piece needed to address a lot of the other pain points that I just talked about. So this work still in the very early stages, but since it underlies so many of the big ticket features, this is going to be our next big target. So this is a high cost, high return kind of thing. And the reason I even bring up the work that we're sort of doing in the lab, is I want to make the point that Java is going to continue to evolve. 3 years ago, a lot of people thought Java was done for. And I think we've demonstrated that we can make significant modernization of the language without compromising our compatibility and without compromising our principles. And we're going to keep on doing that. So thank you very much, and I'm going to turn this back over to Mark.
Thanks, Brian. Push the right magic button here. So, maximize developer productivity. We've heard from Brian about the addition of Lambda to the Java programming language and all the related libraries. That will help immensely to leverage multi-core processors and also just be able to write nicer code even in cases when you're not dealing with multi-core processors. Right now, we'd like to turn to maximizing developer productivity on a different class of devices, namely embedded devices and even teeny embedded devices. This is the Internet of Things trend. So to start off, I think we have a short video to show. Stephen?
Let me grab the video signal or audio signal. Yeah. Thank you.
Pardon us while we rewire.
No. That's a really good video too. Come to the chess demo for that one.
A little teaser. Okay. There we go. Richard Baer, Stephen Chin.
Thank you, Mark. So we're both going to be doing the cool part. Rich and I will be showing cool demos. Rich is the Java client architect at Oracle. I'm the Java Technology Ambassador and Java 1 content chair, although seeing as we're at DevOps, this title seems a little bit inappropriate. I think we should change this, Rich. How about DevOps?
Hey,
Yeah?
while you're at it,
Yeah.
can you make me CEO?
Just for a day, yeah. CEO, Java Client Group. And I'm missing my proper attire. Can someone help me out? Ah, okay. Let me kill the mic so you guys don't get.
Plus, that'll keep them a lot warmer. It's a little chilly up here.
All right, so a little bit better, yeah?
So before we move off into this slide and get to our fun stuff, I just wanted to make a comment about the video that we saw. The Internet of Things is real, and it's already upon us. We've seen for the last year or so, we've sort of seen the momentum building in this space, and I'm convinced that over the next couple of years, we're going to see it take off in a huge way. And Java is very uniquely positioned to be at the forefront of the Internet of Things. Obviously, we've been in the space from the beginning. You saw in Mark's slides the stuff that James was originally targeting with Java was exactly these devices. Java is perfect for this. And so as we go through our presentation this morning on the remainder of this keynote, we're going to show you Java running on a variety of devices. In fact, the entire set.
Yeah. No, I think an important point is that the stuff we're going to show you today it's not just Java ME, it's not just Java SE, it's not just Java on desktop, it's the full stack from back end to front end. And this means as Java developers, you can leverage your skill set across the entire technology stack of what will be the future Internet of Things
and
devices.
Importantly, although it was very very split in the early days, is like ME was a different beast than SE. These changes are being eliminated. We're making a nice, smooth transition across the entire stack so that you can take exactly the things that you know and apply it everywhere. So to start with, we're going to talk about a little toy that was created for Java 1. It's called the Duke Pad. Now, it's a little bit hard to see the actual device. We've rigged it up so that it will be displayed on the big screen. And yeah, your finger has killed the dot.
Yeah, I'm doing it.
There we go. Can we switch to the...
Yeah, I got it. How about that?
There he is.
Duke Pad.
Okay. How come it's not live with the...
That's a good question. Because this guy's turned off. There we go.
In the intervening hour.
This is
since we set it up.
using the Internet of Things to show the Internet of Things.
Do you have the camera? Show it on the camera while
Yeah,
we're...
yeah.
In fact, is it possible to take the camera off and come... Because we've got it all kind of rigged up. It's kind of hard to move the guy around. So the Duke Pad was built on a Raspberry Pi, and you can see the... we need to switch to the camera. Do I have to push a button, or does it do it?
The camera's in the top left.
Oh.
It's left.
Oh.
It's up there.
Oh, there it is. Okay, so you can see this is just
And
some,
it's up on
some
screen
UI.
now, too.
Okay, we got it
We're
up there
good.
now, thanks. So this is just some UI. The DukePad software was written in JavaFX. It's running on Java SE Embedded. If you haven't used Java SE Embedded, it is Java SE, but it runs on ARM. And so it's been available, actually. If you have a Raspberry Pi, you can go download Java SE Embedded and run it on the Raspberry Pi. And the software that we're showing here and everything has all been open sourced, including all the plans and everything else for building the thing. So you've got the DukePad, and there's just kind of this fun little dot for opening it up. And it's basically just a DIY tablet.
I'm going to hold it up for the camera so you can see
the back.
The back edge.
So Jasper Potts and his friends at Oracle in his little lab, they put all this stuff together and just did a fantastic job with it. Worked a lot of hours to put it together. They did the hardware design for the entire DukePad enclosure, as well as figuring out which off-the-shelf pieces to put in here.
Let me point out some of the devices on here. So you can see the actual physical Raspberry Pi here. And we put it at the corner of the case so we could expose as many of the ports as possible to the outside of the wonderful acrylic CNC layered laser cut case. And then there's a daughter board here, which is used for the video to HDMI to power the touchscreen and also get that over USB. There's a Pi camera inside of it. This is a device from the Raspberry Pi Foundation, which is a pinpoint camera for displaying video using the Raspberry Pi. There's a 9-axis gyro accelerometer compass here, a hole for where we will put the GPS in the future, a hole for where the normal DukePad has a battery, but as you can see, this one's been hacked a little bit to make it easier to put up on screen and power off devices, a USB hub, which both does expansion and also is a good place to put a Wi-Fi dongle for giving additional network connectivity. And then one of the really nice features, this is kind of a geeky thing, is there's a GPIO pin, which normally has a serial port here. So rather than attaching to normal pin headers, you can just attach a serial cable to get to GPIO. So you can, that's really the advantage of the Raspberry Pi and devices like this is it's not just a computer. You can use it to interface with the real world. You can hook up I2C devices like door sensors, cameras.
Chess robots.
We haven't had one of those around here.
But yeah, the DukePad, the whole design and everything about it is really as a playground, really, for developers to be able to build something and use it for manipulating all kinds of different things with the GPIO pins and so forth, and really just to have a lot of fun with it. So thank you. Yep, we're good. So on the DukePad, we've got a bunch of different apps here. Some that were sort of in an experimental state, like the web browser. We actually had a build of WebKit on here that worked, but other things like, I don't know. Let's see if our little fossil game guy will come up. And the touch screen and all of the, like I say, all the kits and plans and things like that are online. But I've had some troubles with the little touch guy. See if he'll wake up. Fortunately, you can't see as my fingers pressing that stupid notepad over and over.
I think with any good interface, the harder you press, the more responsive it is. So.
We actually had problems with the touchscreen also at Java 1.
Just get a little edge in there.
And, here, give it a shot. He's not taking my finger.
And it probably also didn't help the fact that I was holding it upside down.
Oh no, you took the screen off.
And fiddling with cables. So this, like any good hardware project, you can see that it's decomposable, it's hackable.
We get like a rating 9 on iFixit or something? I don't know.
Exactly. Not like those proprietary Apple devices. So I think, what is our professional DukePad team? Is this where we reset and we'll talk about our chess demo next?
Yeah, I think that's a good idea. Why don't you do that?
Okay. You want to? We talk through some of the hardware.
Yep.
And let's talk about performance.
Let's talk about the Raspberry Pi and so forth. So this is a link that you can follow that takes you to the OpenJFX wiki, where we've got all the instructions for how to build your own indestructible Raspberry Pi computer. So we were interested in figuring out what is the performance level of a Raspberry Pi, right? So we went on the internet, we did some searching around, and there was various tests that were basically CPU tests, we ran the Raspberry Pi on the thing, and it says, Well, son of a gun, the Raspberry Pi runs at a whopping 250. So we said, well, I don't know, is that good or bad? I don't know, let's try something else like, I don't know, let's run it against a Pentium 2. And the Pentium 2, just barely eked out a victory, but it is definitely a faster CPU than the Raspberry Pi.
At the time Java first came out, I think Pentium 2s were like supercomputers.
Yeah, so
The Java one.
actually works reasonably well.
Yeah.
So then we said, okay, well, that's fine. So you have your Raspberry Pi and Pentium 2, but what about, I don't know, not necessarily one of these, but your sort of typical cell phone class device. How are they relative to, say, a Raspberry Pi? Well, it turns out they're a heck of a lot faster. There's CPU power like all get out, and then of course compared to people are like, wow, these cell phones these days are super powerful. They've got quad core, they're I don't know, gigahertz and blah blah blah, and they are nothing compared to your typical Intel Core i7
computer from even 3 years ago.
So comparing the Raspberry Pi, it's 250 relative to your normal desktop machine, you can tell that there is a huge difference between what these different devices are capable of.
Yeah, and where this shows up most is in the like if you're trying to do things CPU intensive, like compiling stuff on the Raspberry Pi, or trying to do something where you're creating lots of objects or doing things that are CPU intensive. But on the GPU side, it's a whole nother story.
Yeah, and that's really the thing, is that the GPU on the Raspberry Pi is really very good. And it's a trend that's been going on for the last 10, 15 years easy. And the Android and iOS and those guys have really created a market environment where the chip vendors and everybody else have had to push both the GPU and the CPU abilities up. And as a consequence, that whole mobile revolution has created the environment to allow for the Internet of Things. We're no longer talking about running everything on processors that are way slower than the Raspberry Pi, which is typically what's out there in the embedded world today. But the whole market is getting to the point now where you can run some serious applications on these things. So actually, our crack team has got our Duke pad back up, actually.
Yeah.
So let's just
when you know. All right, Fossil Games going
Take a look at a couple things here. Now, one of the interesting things that we'll show you, but we would never show at Java 1, is that you start off running it and you go, holy crap, the performance is bad, right? But just let it play for a second here, and you'll start to see something different. You can see at the point that the hotspot JIT kicks in, the thing becomes actually quite responsive in what it's able to do. And again, this is running on a really, really slow CPU. It's 10 times slower than what you'd see on something like an iPad. But actually, we're able to get 60 frames per second type of performance on it. Oh, yeah, you're gonna get. So anyway, come on now, little guy. So let's go ahead and hide that app. Now, one of the other apps that we wanted to show was the media playing app, which again we haven't, since we rebooted it here, hasn't been pre-warmed. So we'll see the JIT as it sort of figures things out the first time around.
Chug.
So we've got it plugged into media, so we can play media. So all the media support that's in JavaFX will play on there just fine, which is great. And when we really talk about media, what we're really interested in anyway is running some movies. So let's see if we can get the. So one of the other things about the Raspberry Pi GPUs is capable of playing full HD video.
Which is amazing for an old Pentium 2.
Yes, it's amazing for an old Pentium 2. And of course, all the media support is built into it as well. That's a fun movie. And then photo browsing and everything else. So all these kind of, and you can see now as you've been able to watch, as the thing gets warmed up, once Hotspot's doing its thing, it's really quite fast in performance. So that's good. We've got this thing back. That's nice. So let's talk a bit about the demo that we want to show you. So you've got, we've got ourselves a Duke pad. Let's go ahead and connect. Okay, so this machine right here, this Dell laptop, is representing our server, and it's running Java EE7, and it's got a chess server set up on it, and it's using WebSockets in order to connect to various clients. So here we have a a web client. We've joined the chess server. We can see some games that are going on. Now we're also going to run our Duke pad, and it's got chess on there as well. So
why don't you start that, and then I'll flip to the Duke pad screen.
actually, you create the game, and I join you.
Yeah,
Yes.
yeah. So just click on that to switch, and they'll see the chess coming up. I think it needs the magic Richard touch. Oh, there it goes.
Here he comes. Now let's see if he can get a hold of that server. Come on. Alex, come on. There he is. So we've got ourselves some little 3D Duke characters, and that's great. And so the trick here is that since we're on one machine,
Yeah, so I'll make my move
you're just
first.
going to make a move.
I'll just make a move.
Oh. Actually, you're going to have to go create a game, I
Alright.
think.
No, that automatically creates a game. That's what our
Oh,
crack.
you're trying to select the thing.
That's what our crack
There you
team
go.
says. They say press on the touchscreen harder, and it works. Right?
He almost did it. He really thought about it.
Yes.
Okay. How do I, now where's my, oh, here I am.
Yeah, there you are. So
Oh,
refresh the
let
list,
me
and
refresh
you should be
because
able to join.
I need to join your game. Okay, there we go. So let's go ahead and join. All right, now I'm looking at it, and I'm going to go ahead and make my move.
So actually, before the keynote, I was chatting with Jasper, and I was getting chess lessons because, he was beating you up left and right at Java 1, and I wanted to learn his secret technique for winning.
Yeah, I wonder if you can try to set the thing up there, because when you touch, I can actually see the surface flexing
I know.
in the wrong place.
Those are the valid moves. Touch
You're
screen,
never
please.
going to be able to kill me. Oh, darn.
I need a little inspiration there, a little taunting.
Oops, let's get back to our chess client. Yeah, if you think the AV problem we're having here is bad, you should have seen Java 1. Okay. So we can, so basically we've got the two different clients. Go ahead and move your pieces. We've got these two different clients going. They're both talking to the same server. It's Java SE embedded running on one guy. JavaScript talking to the, in the web browser talking to the other guy.
Yeah, the Java backend's actually using cool new Java EE 7 features. We're using WebSockets and a lot of the new APIs, which is really cool.
Okay, so we'll stop there. So some basic chess stuff going on. That's great. Now, you remember on that previous slide that we had the thing where it was like, the desktop was 100 times faster or whatever? So the question is, well, what can you do with all that extra horsepower running on your desktop? So we wrote another chess client. So basically what's going to happen is the other two chess clients that we show, the one that we're going to have here and the one over here, are both basically in read-only mode. So the server has the list of all the commands that have happened so far in the game, and when we play the thing, it's going to start replaying exactly what we saw. So we'll go ahead and bring him up. He'll go full screen for us. So here we've got a JavaFX app with the 3D animated Duke characters, and we saw Duke earlier today, and that's exactly how he walks. and we've put a little fun in here for.
So if I knew he had a hammer like that, I wouldn't have gone so near to him this morning.
You wouldn't have done that either.
Yeah.
So what's cool about this is that we have a professional 3D designer who does the visual design as well as the animations. And he was using Maya, Autodesk's Maya tool, which is basically what's used for doing 3D movies. And he designed the Duke characters and all their animations inside of Maya, and then exported those into Java. So that we have, as part of the OpenJFX open source project, there's a 3D viewer application that has contributions from AMD and some other companies, and a bunch of work that Jasper and those guys have done in order to allow importing of different 3D formats into FX. In Java 8, we've added basic 3D support in JavaFX. And so all this that you see here is all based on what is shipping today in Java 8, in the GA, or in the early access builds and what will be in the GA.
Yeah, and I think that's important to emphasize because we've shown lots of cool stuff in the past at keynotes and like all this wonderful 3Ds and flying videos. But for this demo, this machine was not set up. I literally took the latest version of the chess client, popped the jar in here, latest Java 8 early access build, and it was up and running.
Yep.
So this is all stuff which you can do today with the Java 8 early accesses you can download straight off Oracle's site.
And the thing that I really liked about it was the fact that, again, it kind of goes back into that designer workflow. Some guy gets to produce this in his own tool, export it, and we can just slurp it right up into Java and let it run. So that's cool. Now let's do on the other end of the spectrum. So we've got our EE server, we've got our SE desktop, we've got our SE embedded desktop, we've got our SE embedded DukePad, and then we've got our robot. So we're ready to turn this thing on.
Are you sure you want to press that switch?
I don't know. Do I twist it? Okay, so here we have our robot. And the robot is running Java ME on top of the Raspberry Pi. Now, as he's going here, like I said, he is using WebSockets on Java ME, talking back to that EE7 web server, and reading back the list of moves that we've played, and it's replaying them. The robot has some 8 different motors on it, I believe. There's one at this gear, 2, 3, 4, 5, 6, 7, and there's another one on the base that turns the robot. And they're all being just controlled by these Java ME code, which, if you looked on the bottom of here, is connected from the Raspberry Pi. It's connected directly to this servo motor controller, which then controls all the different motors. Now, the other thing that's kind of cool about this is that, let me grab one of these Dukes. On the bottom, your camera, on the bottom of the Duke, there's a couple little magnets that you'll see in his feet. And you'll notice that each of the different positions on the chessboard and in the little place where the guys get placed have magnets on them. So that way the robot can easily pick them up and move them around. These Dukes were all 3D printed at Jasper's house, I think.
Yep.
And
that was planned.
yeah. And so these guys were all 3D printed, and then they basically used paint thinner, if you will, to create the fumes that would melt the thing so it came out nice and shiny. They also 3D printed the grippers on the robot in order to pick things up. So again, it was really cool. He'd open up like Cheetah 3D, he'd do the design, he'd feed it to the 3D printer, it'd come out, they'd attach it to the robot. They have their computers hooked up to the Raspberry Pi, they punch in a bunch of Java ME code, it starts moving things around.
I think
cool
something
project.
else to point out about the robot and the hardware they're using is that this setup, they bought all the components from Servo City. It's basically hobby level robotics for like little airplanes or devices. It's not something which you'd buy from a professional machine's robotic arm. So it's something which is very accessible to developers. The whole robotic arm components and everything was like 1,000 plus, rather than what they do for industry, which is tens of thousands of dollars to get highly machined parts. And you can do fairly nice stuff with the Raspberry Pi, only $35. Just buying some off-the-shelf servos and motors and gears and stuff, and then putting that together with back-end Java services and even clients to visualize it. One of the first things the team did was build a crane visualization so they could simulate the physics for how they would move pieces around the board before they even started the hardware prototyping of the actual chess table.
Oh, the other thing that I didn't mention was that in each one of the little chess squares, there's, I believe, 16 different LED lights that are in each one of these things, or 4. It's 4 or 16? 4. So there's 4 per each one of these things. And you can actually put all different types of colors in there. And so we were going to program it to say something like, "Hi, Mom," but instead it just kind of gives you red and green where the thing's going to go. But it's also fully programmable.
So I think it's your turn now.
Yeah, how do I get out of this thing? So you've
just
remapped some stuff on me. I don't know how to...
There we go.
There it is. Okay. So now, just to show that that thing is running live, I'm going to make my next move.
Oh no, I'm in
Wait,
check
hold
now.
on for it. Hold on for it. Wait for the guy. Now you're in check. All right.
What should I do? This is I don't know. Maybe I'll take your piece.
Oh, that'll work.
That Jasper told me this always works.
That always works. Get that old queen. So that's, just to, Java ME, Java SE Embedded, Java SE, and Java EE, all, talking to each other, same code, same development experience really across the board. So that's our guy. I can get the slides. So, the bits and should I hit the little button to?
The lighting's nice. Let's leave it running.
Oh wait, we have to get him back into position. His resting position. Okay, there
Very good.
Hey, stop it, you. All right. So, like I said, on our OpenJFX wiki, we've got all the plans and instructions for building the Duke pad and getting started with JavaFX. There's, been a lot of different companies that have been contributing to OpenJFX. It's open source project, it's under the OpenJDK, same project governance and everything else. I mentioned AMD had been contributing some of the 3D importer technology, and also Tessis. And we've had a lot of contributions also from other folks, whether it's about enterprise application development using various different services for like DataFX and Granite DS and so forth for being able to get data to and from your web server. Also, third-party controls from JFXtras and so forth. So there's been a lot of contributions from people in the community. And that's it. So JDK 8, we ship as part of the JDK. One other thing that I wanted to throw in was just that Brian talked about lambdas, and in the context of building these things for Java 1, we were able to really use lambdas, and it really cannot be overstated what a fantastic job Brian and his guys have done to bring this technology to Java. It made writing programs so much clearer and simpler than it was before, and it's not a sales pitch. It's honest to goodness truth. Really excited. They did just a great job getting that stuff put together. And so I'm really excited to see what happens in the future. As we get value types and some of these other things, it'll really make a big difference, I think, to our programming. So Java's here. Java has a real place in this Internet of Things. It's a fantastic opportunity for all of you Java developers. There's a huge opportunity that's coming into the world, and we are all well positioned to be a part of it. And we're looking forward to working with you and seeing you use Java to build all these new pieces of technology. So thanks.
All right, thanks, and please welcome Mark Reinhold back on stage.
Thanks, guys. And now for a quick public service announcement. A big part of what keeps Java going is feedback from actual developers like you. Today I'd like to ask for your help in the final testing of Java 8. In addition to Lambda and Java FX8, there are lots of other great features in this release, including JSR 3.10, the new date time API, the Nashorn JavaScript engine, compact profiles, type annotations, and a whole bunch of other stuff. Java 8, as usual, is being developed in the OpenJDK community. That's where the reference implementation work is done, and in the Java community process, which is where the specification work is done. You can also download the very latest weekly build. There's a new one every Friday or so from jdk8.java.net. We're aiming to ship the release in March of next year. That's not very far away. So please download it and try it out as soon as you can, but don't do it all right now because the Wi-Fi will just melt. So if you only remember one URL from this entire session, jdk8.java.net, check it out when you get home. To sum up then, we've nearly finished the largest upgrade to the Java programming model ever, larger even than generics in Java 5. We're scaling Java SE down to embedded devices and scaling Java ME out to the Internet of Things. There are also lots of exciting ideas, value types, and beyond to work on for Java 9 and later releases. I hope this convinces you that Java is not dead yet. I leave you with the obligatory legal notice. And I thank you very much.